Okay, now if I want to know how H and S vary with temperature at constant pressure, we've done this before. Just to quickly review what we had here, the constant pressure heat capacity shows us how H varies with T. So we have dH over dt is equal to Cp at constant pressure. And then, of course, dH is equal to Cp dt. And again, I can now integrate like you've done previously if you want. If we're going to integrate this, we're going to get delta H is equal to integral of Cp dt from, I'm going to say my initial temperature maybe will be T naught to some new, or we'll just do Ti to Tf. Another way of writing my delta H over here on the left, right, is that is H at Tf minus H of Ti is equal to integral of Cp dt from Ti to Tf. And again, if I want to write this another way, I could also write this that the H at my final temperature is equal to H at my initial temperature plus integral Ti to Tf Cp dt. Not delta, of course, just d. And again, I get that exact same thing for ds. If I'm taking a single substance and changing its temperature, I'm going to be able to use Cp to get ds, because again, dq over dt is equal to Cp if I sort of reversibly heat it from 298 to some new higher temperature. And I get the equivalent sort of equation. ds is d bar q rev over t. Again, I guess if I first do this one, d bar q is equal to Cp dt. ds is equal to Cp dt over t. Not doing all the steps, but just sort of skipping to the ones that we want. Delta S is equal to integral of Cp from Ti to Tf dt over t. Or S, I'll just show this one final one. S at a new temperature Tf is equal to S at a temperature Ti plus integral Ti to Tf Cp dt over t. And you've done that sort of adjustment of entropy for temperature before on the big last exam and on the homework. So this is my answer, but we'll see that there's a slightly better way to write this, right? So the idea here is that if I know my 298 delta H and I now want to figure out it at some new temperature T, I can write out steps just as we've sort of done before. We can do maybe a step 1 where we do the reactants going from hot down to the new temperature 298, then do the reaction at 298, and then go back up here in sort of a step 3 and warm the products up, right? So I could say this here, which I'm going to maybe call, right, if I want to call this like delta RH at some new temperature T, and delta RS naught at some new temperature T. Okay, so when I add those 3 steps together, I have the reactants. Okay, I'm going to use my temperatures here as T naught is my initial temperature. Usually that's 298.15, but not always. Tf is the temperature I'm going to go to. So again, cooling the reactants from Tf back to 298, that's this step right here. This is step 3. This here is step 2. Again, we've done things like this on the previous exam, but again, we're sort of focused on this now, so we'll do this one more time. The molar heat capacity of reactants, the molar heat capacity of products, right? This is correct, but again, it's sort of clunky because of what's going on, all these different steps. We can see that this will be a little bit more convenient if I say that this is delta RH And I'll put circles on these because so let's assume we're doing it at 1 bar of pressure. We don't have to, but whatever pressure we use is okay. Plus T naught to Tf. Now this here, right, you have Cp bar of products. This is that same sort of integral minus, now this thing here, what I'm going to do is, this is going from T naught to Tf. I want to switch those integration bounds, which means putting a negative on it. So when I flip the bounds of integration, I have to switch the sign, and I can do negative T naught to Tf Cp bar of reactants dt. These two terms have the exact same bounds, so I can combine those and get delta RH naught T naught plus, when I combine these two things, I'm going to get Cp bar of products minus Cp bar of reactants. But now this Cp bar of products minus Cp bar of reactants, this actually is just another quantity associated with the reaction. So this thing here, we can write a lot more simply as delta R Cp of my reaction. And again, if this is done at standard conditions, this would be delta R Cp with a little naught on it. I don't know, a lot of times we're not as, again, a lot of times we won't include the naught there. But because usually Cp doesn't depend very much on pressure, but if it does, we can include that naught there. And we can do that integrating with respect to T. And that's a nice final way of writing it here. So we can just use the delta H's to figure this out. An easier way of doing this here is to write delta Rs naught, is to go back here and use sort of our delta arithmetic right on this equation. So if we have our S's here, it's actually perfectly valid, and we'll see that this makes the math a lot faster and easier to go in here and to say, okay, I'm allowed to apply this true fact to a chemical reaction. And when I apply that to a chemical reaction, what I'm going to do is I'm going to replace extrinsic variables, thermodynamic variables, with delta Rx. So any extrinsic thermodynamic variable x will get replaced with delta Rx. So again, for S here, that's the thermodynamic variable, so I'm going to say delta Rs of Tf is equal to delta Rs of Ti plus Ti to Tf. Cp is intrinsic, but of course, or a T is intrinsic, but then I also have delta Rcp over T dt. And that's the analogous equation for adjusting the entropy here. So what I need to do is just figure out delta Rcp of the reaction, and then I can adjust H and S according to these equations. So and again, these are nothing really new. This is the exact same thing we would normally do to adjust entropy for a temperature change at constant pressure, right? This is constant pressure And similarly over here, right, this is a constant pressure type of change, how I can adjust. At constant pressure, how can I adjust the entropy of a reaction?